Hey folks, let's talk about molecular orbital theory. Molecular orbital theory is a more sophisticated way of describing how atoms come together to bond and form molecules. Now, because it's more sophisticated, it is both more powerful and a lot more complicated. We're going to start just with kind of the basics in this video, and then we're going to elaborate on them in class. So let's start thinking about what molecular orbital theory is. Okay, what molecular orbital theory does is it describes the coming together of individual atoms that each have their own atomic orbitals, and it considers that those atomic orbitals combine to mix and blend and form a new set of molecular orbitals. There are some rules that help govern those molecular orbitals, and trust me, we're glad we have them. So here we go. First rule. The number of atomic orbitals that you are combining is going to be equal to the number of molecular orbitals that form. Second, orbitals can overlap in one of two ways. They can overlap in a constructive manner to form bonding orbitals or a destructive manner to form antibonding orbitals. Third, your atomic orbitals combine most effectively with other atomic orbitals of similar size and energy. Fourth, each molecular orbital can accommodate at most 2 electrons with opposing spins. Fifth, when you're filling your orbitals, you want to fill them following Hund's rule, where your electrons are going to fill orbitals of similar energy singly before you pair them up. The sixth and final rule is that when it comes to the energy of the molecular orbitals that result, the greater the overlap of the atomic orbitals, the lower the energy will be, and the less the overlap of the atomic orbitals in the resulting molecular orbital, then the higher the energy will be. We're going to take a look at 2 specific examples to see how these play out. First, we're going to start with bonding and hydrogen. Hydrogen is a great place to start because it's the simplest of our possible molecules we can make. Each individual hydrogen atom has 1 electron and 1 proton. And so if we envision those atomic orbitals, which we know that our hydrogen is in a 1s orbital, we can talk about taking our 1s orbital, which is spherical, combining it with a second 1s orbital. And since we're combining 2 atomic orbitals, we're going to get 2 molecular orbitals out. Now the energies will always, the total energy will come out to be the same. So one's going to be more stable, lower energy, and one's going to be less stable, higher energy. And so the change in energy, like the net change in energy is 0 because you've got those 2 different orbitals. Now, these orbitals can overlap in a constructive way or a destructive way. Because for this understanding, we have to think of our electrons in the orbitals as behaving as waves. We'll talk more about this in class. When the orbitals come together in a constructive interference method, constructive interference way, you end up with the electron density concentrated between the 2 nuclei, and you have what we call a bonding interaction, and this forms a sigma bond because the electron density is concentrated on that internuclear axis. And since this was formed by the combination of 2 1s orbitals, we call this the sigma 1s. Well, every time you have a constructive interaction, you also will have a destructive interaction. So if here are my nuclei once again, the destructive interaction results in the electron density being found outside primarily of where the atoms are, and what we call a node or a nodal plane between the 2 nuclei. This is not energetically favorable, and it's what we call an antibonding or sigma star orbital. And since it is from the 1s orbital, we will call it a sigma star 1s. So antibonding, bonding, and the sigma represents that electron density is concentrated along the internuclear axis or is excluded with your nodal plane from that internuclear axis. Guys, a node or a nodal plane is where there is 0 probability of finding your electron density. That's what it means. Okay, so here are my possibilities. We often represent this with a molecular orbital diagram, which looks kind of like our orbital diagrams when we were doing them for atomic orbitals. Let me show you what that looks like. For these, we typically set it up where we have each atom we're starting with and their electrons separated. So we see I have one atom with one electron in the 1s and another one with an electron in the 1s. And then when these combine, we are going to demonstrate that we have a bonding orbital with lower energy. This is my sigma 1s. And then I have an anti-bonding orbital that is my sigma star, 1s. And you will often see these connected with dots or dashed lines so you can see where they came from, which atomic orbitals combined to form these new molecular orbitals. And when I go to place my electrons into these new molecular orbitals, we're going to follow all of our same filling rules. You're going to start from the bottom and fill your way up 2 electrons per orbital. 1, 2, and so I only had 2 electrons. I'm done. Now, I have electrons in my bonding orbital and none in my anti-bonding orbital. This signifies a strong bonding interaction. We can actually calculate our bond order from looking at a molecular orbital diagram, because my bond order is going to be equal to the number of electrons that are in a bonding orbital minus the number of electrons that are in an anti-bonding orbital. And then we're going to divide by 2 since 2 electrons form a bond. And so we can see here for our example over here, I have 2 electrons in a bonding orbital, none in an anti-bonding orbital. And so I have a bond order of 1, or a single bond between my hydrogen atoms, which is what we typically think of when we draw an H2 molecule with that single bond. There's hydrogen. Let's take a look at the bonding in the second period elements, and we are specifically going to take a look at nitrogen. We will talk about the others in class because there's nuance here, but let's just start with one. Okay, nitrogen has electrons in the 1s, the 2s, and the 2p. We've already seen how the 1s overlaps. The 2s overlaps in the same sort of way where you have a sigma bonding orbital that forms and a sigma anti-bonding orbital that forms. But now we've got p orbitals. Okay, this is where things get exciting and interesting. Remember what your p orbitals look like. They look like those little dumbbells, and that there are 3 of them, and they are oriented along the x, y, and z axes. So if you imagine 2 nitrogen atoms with these p orbitals coming close to one another, they're going to overlap differently depending on whether those p orbitals are facing towards one another or whether the ones go up and down as they're kind of coming in side to side. Let's take a look at each of those possibilities. If you have the p orbitals that are along the internuclear axis, then these are going to overlap in a head-on or end-on sort of fashion. And so similar to what we saw with the s orbitals, we're going to get sigma bonds forming. We're going to get a sigma star where I have more electron density concentrated between the 2 nuclei from a constructive interference of those atomic orbitals. And so this would be a sigma, and we're going to call it a sigma 2p because it's from those 2p orbitals overlapping. And I'm also going to end up with a sigma star. So again, I'm going to get a nodal plane between the 2 nuclei, and my electron density is going to be concentrated away from that bonding region. And so this is a sigma star 2p. The ones that are overlapping head on, those are a little more interesting. Okay, when these overlap, again, you're going to get 2 different types of bonding interactions. You are going to get a constructive bonding interaction and a destructive bonding interaction. But now my electron density is actually above and below that internuclear axis. So in the constructive form, I get electron density above and below the axis, but between the 2 nuclei. And so this is a pi bonding interaction, so we'll call it a pi 2p. And then the anti-bonding, again, has a nodal plane between the 2 nuclei, and so it ends up looking something like this. I always think this one looks kind of like a butterfly. But this is my pi star anti-bonding interaction. And there's 2 of these because you've got p orbitals that are overlapping sideways this way and ones that are overlapping sideways this way. So what does my molecular orbital diagram look like for nitrogen? I'm going to draw it and then we're going to talk about it. Okay, each nitrogen has a 1s orbital, a 2s orbital, and 3 2p orbitals. So we're going to do this twice. Okay, and nitrogen is 1s2, 2s2, 2p3. So let's put those in there so we remember how many electrons we're going to ultimately have to work with. Okay, here we go. Time to overlap constructively and destructively. My 1s orbitals are going to overlap, forming a sigma 1s and a sigma star 1s. Okay, my 2s orbitals are going to do the same because s orbitals always overlap in a head-on way. So you get a sigma 2s and a sigma star 2s. Okay, I'll use my little dashed line so I can tell where those new orbitals are coming from. Now, my 2p's, they're going to interact in different ways. They're going to interact to form the sigma 2p, but also the pi 2p. And the sigma formed a sigma star. That was kind of equally high as that one was low in terms of energy. So we've got overall net zero change in energy. And I'm going to have my pi stars from my 2p orbitals. So these guys do multiple things. Yeah, it's really busy. Kind of regretting putting those dashed lines on there, but they're usually drawn to show where they came from. Okay, so there are my molecular orbitals. I have an equal number of molecular orbitals coming out as I had going in. Let's put our electrons in. I'm changing color so we can see them. I have a total of 2, 4, 5, 6, 7 electrons from each atom, total of 14 electrons. Here we go. 1, 2, 3, 4. Still fill from the bottom up. 2 electrons per orbital. 5, 6, 7, 8, 9, 10, 11, 12. Fill singly before doubling up. 13, 14. Okay, there we are. We've got them all filled. This is what our molecular orbital diagram looks like for nitrogen. Now I want to do one last thing. I just want to calculate bond order, and we're going to call it done, and we'll talk more about stuff in class. Remember to calculate your bond order. You are going to take the number of bonding electrons minus the number of anti-bonding electrons. So bonding electrons, 2, 4, 6, 8, 10. So 10 bonding electrons minus anti-bonding electrons, 2, 4. 4 anti-bonding electrons. Take that, divide by 2, we get a bond order of 3. Nitrogen forms a triple bond, and we're familiar with that fact. And so we typically will draw its Lewis structure like this. And so we see that triple bond between the nitrogen. Lots more to talk about. We'll talk about it in class. I think this is enough for one video.